Good morning. Today we're going to be talking about groundwater. So this unit, geomorphology, we started looking at weathering and erosion and or the breaking down of the rock and then the transport of that material. So now we're going to be, and then we talked about soil. Of course, soil is the collection of that material that's been weathered and dropped off somewhere, and then it piles up over time along with organic matter to create soil. So today, what we're going to be talking about is groundwater, how that, the amount of groundwater that is on the planet, but also how that water moves from different parts of the water cycle into the ground and how we get back to it and some of the things that can affect the quality of that groundwater. So let's get right to it. So first off, a quick review of the planet's water. So when we look at the hydrosphere, we can divide it up into freshwater and saltwater, of course, is the easiest. Of our planet's water, about 97% of it is saltwater in the oceans. I'll show you a graphic here in just a second to visually represent that, but the hydrosphere is about 97% saltwater. The remaining 2.83% or so is your freshwater. So very small amount of usable fresh water on the planet. Most of that water is locked in glaciers and ice. Only about 0.62% is going to be groundwater. So all the other freshwater lakes, rivers, streams, it's actually a very, very, very small percentage. So overall, freshwater, very small. Groundwater makes up a pretty large portion of that freshwater. This is a graphic representing all of the planet's water. So we think we have this water world, this blue world, and that's true, but the ocean is really just a really thin skin on the planet. So when you take all of that water and you pile it together into a sphere to compare it to the rest of the planet, you'll see that it's actually pretty small. It's about 1,000 diameter ball of water. That's all of our water. All of our fresh water is much, much, much smaller. You can barely see it in the graphic. And that, of course, includes mostly glaciers, but groundwater as well. And then if we just looked at the freshwater in rivers, lakes, it's tiny. It's very, very tiny. So all of that usable fresh water that we think we have, it's really a very small amount. So it's a resource that we have to protect, just like our soil. So a quick review of the water cycle. Water cycle, of course, explains how the hydrosphere constantly transports material from the atmosphere into the geosphere and then biosphere as well. So how water moves through all of those different systems. Of course, you have evaporation and precipitation. You're very familiar with those, I'm sure. Runoff. So some of the water coming down from precipitation actually runs back off into the ocean, but a lot of it actually goes through infiltration into our groundwater. So water is the predominant agent of erosion. Rivers transport more sediment than any other source of erosion. It is also the main ingredient for most chemical weathering. So water is extremely powerful. So a watershed, hopefully you've heard of this term before, but a watershed is an area or piece of land that's drained by a river or basin or a sea. So a watershed, you can think of it as an area of land that's all drained by the same body of water. So water that's not filtered and stored in the ground actually becomes part of the watershed as part of a river or stream or runs off into the ocean. So as I said last class, really want to think about the terms porosity and permeability. So let's talk about porosity. So groundwater is water that moves through pores in soil and rock, permeable rock. Groundwater, of course, is an important source of fresh water. We pull most of our well water from, or our usable water in our homes from the groundwater. And that's partly because it's been filtered by the rock and material down below us. And so that by the time that we get it from the ground through a well and a pump, it's very clean. So groundwater is water that fills and moves through those open porous spaces in the ground. An aquifer is the area where that groundwater is stored. You may have heard this term before, aqua, of course, meaning water. So an aquifer is where that groundwater is stored. So back to porosity and permeability. Porosity means the space in between different particles of sediment or material where groundwater can fill in. So the greater the porosity, the more water can be stored in the aquifer. It's the sorting of the sediments that determines the porosity of that material and how much water can be stored in the ground. If the sediment is well sorted, and what I mean by well sorted is by size. So well sorted is about the same size sediment. So if it's well sorted, the porosity is going to be improved. It'll hold more water. And you can look at the graphic here. The well sorted coarse grained sediment has a high porosity. Well-sorted fine-grained sediment also has a high porosity equal to that of the coarse-grained. And then it's the poorly sorted material where we have lots of different sizes of material that has a very low porosity because the small pieces can fill in between the big pieces, and so it doesn't hold as much water. So well-sorted equals high porosity. Poorly sorted, lots of different sizes, is low porosity. Permeability. Now, permeability is the rate or the ability of water as it passes through a porous material. So pores or fractures must be connected for there to be a good permeability so that it can continually flow through. Rock is considered porous if it has lots of empty spaces that can fill with water. Rock is considered permeable if those empty spaces are connected and allow water to flow from one space to the next. So the sorting of sediment also affects how water flows through the ground, not just how much water is stored, that's porosity, but how water flows through the ground is its permeability. Larger and well-sorted sediments will have a high permeability. So lots of big empty spaces, the water is able to flow through very easily. We talked about this a little bit last class. So if you have a bunch of gravel, water is highly permeable. It will flow through very quickly. If you have sand, the permeability is going to be lower, but the water will still be able to travel through. So larger and well-sorted have a high permeability. Smaller sediments and or poorly sorted sediments is going to have a low permeability. If you think of like clay, clay is such small particles that the water is not going to be able to move through very quickly. So it has a low permeability. If you were to mix that clay with a bunch of gravel, again, the clay is going to fill in a lot, all those empty spots. And so it as well is going to have a very low permeability. Water is not going to be able to move through very rapidly. All right, so let's talk about some parts of our groundwater systems. There are different zones, and they're based on how much water is there. So basically, we have two main zones. We have the zone of aeration. It's found above the water table. The water table is the line where water is going to be stored below that line. Above that line, water is not going to sit there. It can move through. That's the zone of aeration. It's where water moves through on its way to get to the next spot called the zone of saturation. It's below the water table, that line that separates where water moves and where water is stored. That's the water table. So where the water moves is called the zone of aeration. It doesn't hold water, water moves through it. And then the zone of saturation, and that's where water is stored. That's where our groundwater is stored, and that's where we have to access to get fresh water for our wells. You'll also notice in this diagram, we have something here called an aquitard. An aquitard is a layer of impermeable rock, so water cannot move through it. That kind of sits in a zone of aeration or a zone of saturation. So groundwater is continuously used and replaced by the water cycle. It's necessary for life, of course, but is groundwater renewable? What does it mean to be renewable? Is it depleted when used? So consider that water, when it becomes contaminated, can it be replaced or recycled in less time than it takes to be used up or destroyed? Just like any other resource, like coal, which takes millions of years to form, compared to the hours it takes to consume it. So the Earth is making coal now. It's just that we're using it up at a faster rate than it can be produced. That's what makes it non-renewable. So is groundwater renewable? Can it be filtered and move through the zone of aeration into the zone of saturation fast enough, at a faster rate than we can use it? What about water that's contaminated? Can it be cleaned and filtered naturally through permeable rock in less time than it takes to contaminate it? So we really have to think about groundwater as a non-renewable resource because we can use it faster than it can be replenished. So groundwater may come from a watershed. Remember, all water in a watershed drains to one local source. So if that water becomes contaminated by waste dumps, chemical storage, fertilizers, pesticides, leaking sewer system, it can leak out on the ground or it can leak into our groundwater system. Either way, all of that water in that watershed is going to be contaminated because it's going to mix with all the other groundwater. All right, so let's just talk a minute about how a well works. So there are two main types of wells. One's called an ordinary well, and one is called an artesian well. So in an ordinary well, you have basically a straw-like tube that goes through highly permeable sediment or rock and pushes into the zone of saturation. So it goes through the zone of aeration into the zone of saturation below the water table. As it pulls water up, the water will form a cone of depression. So just by sucking it up, it forms a cone. Makes sense? Once you stop pumping that water, it will, of course, go back. But as you're pumping that water, it forms this cone. So let's take a look at this interactive and just kind of move through it. All right, let's enter the subterranean world of groundwater. So dig deep into the ground and you'll probably find groundwater. It fills the smallest spaces in between bits of sediment and rock. Remember, porosity. It's almost everywhere, flowing beneath your feet, under your home, cities, farms, deserts. Many of us drink groundwater every day. So why is it there and how do we tap it? So reservoirs of groundwater exist as long as enough rain seeps into the ground. Many groundwater basins of different sizes exist around the world. Today, many groundwater basins are shrinking and others are being contaminated. Because people rely on groundwater, it's important to understand how these systems work. So when we look at this sediment under this looking glass, you can see that there are porous spaces in between the sediments, porosity, and these different sediments or grains. And so as the water permeates through this, because it has these porous holes or stored spaces, the water is permeable and able to move down. It moves down below the zone of aeration, that's the brown part here, into the zone of saturation, the saturated zone. That line that divides the two is called the water table. So as groundwater begins as rain, it seeps into the ground, flowing through the zone of aeration into the zone of saturation. Once inside, it continues to flow very slowly, sometimes leaking water into local streams or even directly into the ocean. Of course, contaminants, naturally dissolved materials can move into those systems. So let's take a look at the water cycle. So of course we have rain, precipitation. Infiltration is the movement of that water from the ground into, from the surface into the ground. And it's constantly replenishing that zone of saturation. You can see how it rises after the rain and then after it stops. it drops down. We have evaporation from the rivers. That's going to pull water from those sources, including groundwater, and pull it up into the atmosphere. So again, it's raining. The river is going to get larger, and the water is going to move through the zone of aeration into the zone of saturation below the water table. A well. Groundwater is good for drinking, watering crops, bathing, and much more, but how do you get it to the surface when you need it? You make a well. A well is a straw-shaped hole that reaches from the surface into the groundwater reservoir. You drill the well, install a pump, turn the power on, and voila, the water comes out. So let's drill our well. You can see it goes into, below the water table, into the zone of saturation. And as it's pumped, it forms this cone of depression. If you pump faster, the zone will become bigger and bigger. That cone of depression will become bigger and bigger. And if you stop pumping, of course, it will return back to normal. Notice in this diagram, you also have this thing called an aquitard. It does not allow water to pass. So if you are trying to pump water out, you have to be on top of that aquitard or below it. You're not going to be able to get water from inside of it. So that's basically it. Groundwater is, like I said, is pretty much a non-renewable resource. It's extremely important. Water moves through all of those different systems, and we all rely extremely heavily on it. All right, let's get back to our presentation and continuing on. Now, an artesian well is slightly different. I just wanted to expose you to this. An artesian well is basically water that's under pressure, so it doesn't require a pump. And how that works is you have this ordinary well that can go into water that has been pressurized. Maybe there's an aquitard that's sitting on top of it and it's putting pressure on that water. And so it just allows it to come up by itself. You still have the cone of depression. You can still get contaminants from runoff from fertilizers, pesticides, or the big thing here, though, is you may not have contaminants that get through that aquitard, that cap rock. So you primarily have contaminants from other sources, but artesian well, water under pressure. So let's kind of wrap things up with a quick talk about weathering and erosion. So water, of course, is the biggest erosional factor. It moves more sediment than anything else, but water is also the primary ingredient of chemical weathering. Some of the things that it can create through hydrolysis and carbonation, chemical weathering, are things like caverns, stalactites, stalagmites, sinkholes, natural bridges, which we have here in Virginia. So again, I want to talk to you just for a second about something called karst topography. Karst topography is a very special type of weathering on limestone. Limestone is very susceptible to acids, including groundwater that is acidic due to carbon being dissolved into it. So it becomes carbonic acid. It's a weak acid, but it can dissolve the limestone and move that material, erode it from one place to another, creating sinkholes, caverns, things like that. It also prevents, when you have karst topography, it also prevents groundwater from being purified naturally. And the reason is because you have all these big empty spaces. Now the water that moves through into these caverns and big holes, big groundwater storage basins, basically, it's not in sediment, it's open. And so the water is not going to be purified as much. That's one of the big problems with karst topography and using groundwater systems. The water is going to collect and not move through those permeable areas as much, and so the water can become contaminated much more quickly. Here's an example of a sinkhole created by carbonation of limestone. Yeah. Here's one in Guatemala. It looks fake. It is real. Now, some of these sinkholes, of course, can form as limestone is dissolved. It could also occur because water leak underground can erode the sediment there and break down the limestone as well. But sinkholes can be quite a big problem. Here's that sinkhole up close. Real briefly, let's talk about Florida. So why does Florida? Florida has a lot of sinkholes. This map is reported sinkholes since 1954, and you can see the location of those, and there are a ton of them. So why do you think? If you answered limestone, you would be correct. It's the geology of Florida. So the state has a lot of limestone underlaying the soil, primarily susceptible to carbonation and, of course, the formation of karst topography. Here's a really neat one. This is called the green banana hole. Blue holes are areas that are in shallow ocean where the underlying rock is limestone, of course, has been eaten away through carbonation, and it leaves these huge, it can leave huge, basically sinkholes, but they're blue because they're sitting in the ocean. They're very deep, and they can be very deep. This one is about 50 miles off the coast of Florida. It's about 154 feet and extends about 427 feet down. Blue holes in this area are thought to have formed as sinkholes on land about 8,000 to 12,000 years ago due to lower sea levels, and then as sea level rose, it filled in with ocean water. All right, so again, groundwater, a non-renewable resource that deserves protection because it is something that, of course, influences the biosphere, moves through the geosphere, is part of the atmosphere, and of course the hydrosphere. So just wanted to add to your knowledge about groundwater. Hopefully you learned quite a few things, and that's basically it. If you have any questions, as always, please let me know. Thank you so much.